All you got to do is post the links on social media. They'll go viral. Everybody wants to see it, right? All right, here we go. A rectangular schoolyard to be fenced in using the wall of a school. Here it looks like the school to me. Does it look like to y'all? And it's a rectangular schoolyard. That's pretty much a rectangle. 150 meters of fencing for the other three sides. The area, A of X, that's A of X right there, in square meters of the schoolyard is a function of the length X in meters of each of the sides perpendicular to the school wall. Perpendicular means, if you want to turn out the light, you can. Perpendicular means right angle with the school wall. So this is X here on both sides. And we started with 150 meters. And so we started with 150 meters. Oops. I think there's a light on there somewhere. There's supposed to be a light on there somewhere. Ain't no, there's the light. All right. You made it worse? Can you see that? All right. I'll try to see it too then. If we used X meters here, we took away X from it. And if we used X meters here, we took away X again. And so that leaves us for this side 150 meters minus 2X meters. That's the rectangle. That's the dimensions of the rectangle. So an expression for the area of this rectangle, area is the space inside, is length times width, or X times 150 minus 2X. And it says, what is the area of the schoolyard when X equals 40? So that means we're going to take this function A of X and we're going to plug in 40 for X. And that's 40 times 150 minus 2 times 40. What's 2 times 40? And so it's going to be 150 minus 80. What's 150 minus 80? That's 40 times 70. And if you take your calculators and punch on it, that's 2,800. And this is meters, areas in units squared, so it's meters squared. And then it asks us what's a reasonable domain for A in this context. This is kind of like we talked about with our poster and our box a while back. We got to use X. What are the reasonable values for X? If we don't come off the wall at all, let's say we laid the whole 150 meters of fence right up against the wall, would we have a pen? A schoolyard? So that means that our X has to be greater than 0. And how long could we make X? Remember, we're using it here and here. Before we used up our whole 150 meters. Yeah, if I use 75 on this side and 75 on this side, I got nothing left. So I can't make a schoolyard. So it's going to be less than 75. That's how you do number 1. That's 3-minute video, but I can't put on just 103-minute videos because that would take me too long to upload. The next problem says Noah finds an expression for V of X that gives the volume of an open-top box in cubic inches in terms of the length X in inches of the cutout squares used to make it. Now this is our box. Y'all remember our boxes? Seems like a long time ago. Maybe last year or maybe when y'all was in kindergarten. I'm not sure. It seemed like a long time ago, didn't it? Right? We took a poster board and we cut out X. Squares, X by X. And then we folded the box up, made us an open top box that looked like that, right? So he came up with a function, V of X, based on his box. And this is the graph it gave him. And he figured, graphed it from -1 to 5. That's -1 to 5. So this is the graph he gets. What would be a more appropriate domain for Noah to use instead? Remember, The y value of these points on the graph represent the volume. So look over here to the left of 0, between 0 and -1. What do you notice about the y values on the graph? They're less than 0. They're negative. Does it make sense to have negative volume? Does not. So why don't we start this at 0? And then, here we go. The volume's going up as x gets bigger and bigger and bigger. And when it gets to 1 something, a little bit past 1, it looks like it's going to get as big as it's going to get. And then go back down when we get bigger x values until we get to here. And what's the volume here? Well, the 2.5 is the size of the x cut, right?
Zero.
The volume's 0. Do we want 0 volume in a box? No, so we really don't want to keep 2.5 there. But what happens when your cut gets bigger than 2.5? That doesn't make any sense, does it? So what do you think our top value for x ought to be?
2.5.
That looks reasonable to me. What's an approximate maximum value for this box? That's going to be where the maximum volume occurs, and it's going to be about 15. And this is in inches. And when we're doing volume, what do we know about the dimensions? They're cubic units, right? Do what? Sorry, yes, you got to tell me that because I can't say that. Good. Let's do one more on this video. Here we got Tyler. That was Noah before. Now we got Tyler. He does another one. Got him expression V of x. Volume of an open top box in cubic inches in terms of length x and inches of the square cutouts used to make it. Same scenario as before. Same pictures. Different graph. This is the graph Tyler gets if he allows x to take on any value between -1 and 7. What would be a more appropriate domain for Tyler to use instead? Start at 0 because volume's negative over here, isn't it?
Yes.
Then where?
3.5.
Right about 3.5, it hits 0 again, right? We don't want that. So it's got to be less than 3.5. Negative, we don't care about all that. Over here, it isn't going to apply because we've used up all the poster board. Won't even have anything to cut that big. What's an approximate maximum volume for this box? Occurs right there. The y value is about 55. 55 what? Inches cubed for volume. Square for area, right? All right, that was painless. That's an 8-minute video. I think it's pretty good.